Well, thanks, Dan, for that nice introduction, and thanks to all of you for the invitation here today. So I'm going to be talking about a study here in the Northern High Plains Aquifer about climate change effects on recharge. Is the volume okay? Okay. So you're going to be seeing more images of, these are one of our recharge vadosone installations, and this one's in rangeland setting in the western Nebraska. So first of all, this was a collaborative project, and first and foremost, I want to thank all the landowners for giving us permission to put these installations in their fields for what's turned out to be 10 plus years in some cases. This was work originally with Dwayne Woodward, who's since retired at Central Platte NRD. Greg Steele was originally part of the program as well. He's since retired, living the good life. But Brandy Fleer, I want to thank, and Chris Hobza at USGS. And what I'm going to present today was some work from a master's student of mine, Zach Luffenberger, and then funding at the bottom from the Water Sustainability Fund, Environmental Trust, and others. Okay, so I'll start with a very brief introduction and motivation for some of this work about challenges around groundwater sustainability and how it fits into the water, energy, food nexus. Then most of the talk will be about this study in the Central Platte NRD, it's a field and modeling study of how climate change may affect recharge throughout the NRD. And since I'm coming from California, and this series I think is on NRDs and water management, I thought I'd end with a little bit of news of what's going on in California with the new Sustainable Groundwater Management Act. It's a big deal in California, so I'll end with that, and hopefully it'll be of news and interest to all of you. Okay, so some of the motivation for this work about groundwater sustainability and the impacts of climate change. It really fits into this concept of the water, energy, food nexus, which has really been increasing in sort of the research world over the last 5 or 6 or 7 years with programs like NSF and FUSE. But it's really a response to some global trends in terms of population growth. We'll have 11 billion people by the end of the century. Poverty, there's still over 1 billion people that lack access to clean water and food security. Urbanization, we have a lot of us, growing number that live in urban areas, over 66% by mid-century. And then, of course, the effects of climate change on hydrologic cycle, how we produce food, and energy consumption. So within this context of the water, energy, food nexus, there's this growing demand for water, energy, food that's estimated to increase by about 40, 50, and 35% respectively, just by the year 2030. And those demands increase as we progress throughout the 21st century. So there's some big questions about how do we deal with this growing demand for our water and our food and our energy. So if we think about our planetary boundaries and the fact that there's this growing demand for water, energy, and food, and we have our water and energy food that provide fundamental goods and ecosystem services, what we're seeing is a growing amount of conflict and trade-off because of climate change, socioeconomic development, and we're seeing growing conflict and trade-off specifically around water and food and the decisions we have to make during drought about allocating water for environmental flows versus water for agriculture. So we're going to talk about this global groundwater crisis in a minute. And also some images here from California. There is a tremendous amount of energy that's used to transport water, to clean water. And we also use a lot of water for energy production, hydroelectric or hydraulic fracturing, which is here in the Central Valley. So this idea about the global groundwater crisis has come into the literature over the past several years. Jay Femlegetti, I guess, has coined the term back in 2014, but it's something we've known about for decades. It's this idea that specifically in arid and semi-arid aquifers, we're losing groundwater storage, mainly because of over-abstraction. Just to show a few figures here from some of the largest, most productive aquifers around the world, like the Guarani, the Southern High Plains, in Australia, the North China Plain Aquifer. And the High Plains Aquifer has been estimated to have lost about over 12 cubic kilometers per year over this period of 2008 to 13. Text is hard for me to read up here. So there's this growing concern about how sustainable our groundwater is. The real challenge with groundwater sustainability, it's not so much that we're overpumping, it's largely because we're pumping fossil groundwater resources, water that's recharged in many aquifers thousands of years ago. And on the left we have, you've probably seen maps like this. This is the decline in water levels in the High Plains since pre-development. Most of the declines, upwards of 40 or 50 meters, have been in Texas and Kansas. Fortunately for Nebraska, the problem hasn't been as severe. There's areas where there's been increases in water levels. But we've done, this was about 10 years ago, we did some dating of the water in some of these locations and estimated using carbon-14 the apparent groundwater age anywhere from 5 to 6 to upwards of 10,000 years. So in many of these aquifers that are supporting these large food systems, we're heavily pumping water that has recharged many thousands of years ago. And what we see is basically in the High Plains, a very thin veneer right at the water table of recently recharged groundwater. So this is the challenge. We're overpumping this fossil groundwater. And it's not just the High Plains, but the Mississippi Embayment, the Central Valley Aquifer in California. So there's a lot of big questions about the projected life expectancy of these important aquifers for food production. How can we manage, slow, mitigate some of these depletion trends? And so the simple answer, we need to think about the water budgets and how we manage these systems. And today, I'm just going to be focusing on the inflow or the recharge to our aquifers. So I think it's really important when you think about research questions that we often scope and have the scale consistent with management scales. And it's really important to understand how land use and land cover and specifically climate variability and change can influence recharge rates. It's important when we're building groundwater flow models and making management decisions, especially in these irrigated agricultural settings. So the questions we're going to tackle today, how does the land use land cover, and we're going to focus just on recharge, or rangeland and irrigated land affect recharge rates, and how might future climate change affect precipitation, irrigation demand, evapotranspiration, and ultimately recharge. And a lot of this work in the Central Platte originally was motivated by the Coheist model that was grew out of the three-state cooperative agreement, and there was questions about recharge rates in the Coheist model. And so we're going to get to the study in just a minute, but the recharge mechanisms we're going to talk about today, we can think about maybe 4 main categories of recharge mechanisms. Today we're going to be focusing on irrigation return flow or irrigation recharge that happens when water flows below the root zone beneath agricultural fields, and also think about diffuse recharge, which is sourced from precipitation. The irrigation recharge can be from irrigation water and the additional precipitation. In the High Plains, focus recharge is also an important mechanism. We're not going to touch on that today, but whether it's beneath ephemeral streams or playas, focus recharge is important. And then mountain block or mountain system recharge, we won't touch on that today, but other parts of the West is very important. So there's a lot of questions that have been starting to be addressed in the literature about how future climate may affect recharge. The general rule is the warm areas will become warmer, the cooler and wetter areas may become cooler. It's going to have a significant effect on our snowpack across the western US. There might be more intense storms, rain events, more runoff. So we may see more higher discharge, maybe more focused recharge. Possibly that could mean if there's more runoff, less diffuse recharge in some settings. And then there's a lot of questions about how farming practices may change to future climate and what that might mean for more or less irrigation recharge. So to address some of these questions that specifically in the Central Platte NRD, We followed an approach that we used in the USGS NAWQA study that I was a part of from 1999 to 2008. This was part of the USGS's effort to understand the status, trends, and process level understanding of water quality in important watersheds and aquifers around the US. And we used a source transport receptor conceptual framework for this project. And so to understanding sources of contamination, we used a series of vadosone installations that I'm going to go over in a minute, and a lot of monitoring wells that were screened under different land use types. And I've spent a lot of time in the high plains. I'm in California now, but we sampled hundreds of wells from Texas up to Nebraska. So I'll show you the report if you want more information about the NAWQA study in just a minute. So originally, with the NAWQA study, we were interested in recharge and controls of recharge, specifically land use, land cover, and the north-south gradient and average annual air temperature. So we had these vadosone installations in Texas and in Kansas and in Colorado and western Nebraska. And primarily they were installed under irrigated fields and rangeland fields. And the project in the Central Platte, we wanted to know how the east-west gradient and average annual precipitation might also be affecting the recharge rates. So we're going to go through this in a minute, but we have the data collection and data loggers at land surface, weather stations, monitoring wells at most of our sites, and then we have very detailed data collection throughout the vadosone in terms of soil hydraulic properties, different chemical tracers, and we can collect pore water and heat dissipation, matrix potential data. So to zoom in on where these sites are located, here's the Central Platte NRD outline here. And so we have sites in irrigated corn in the eastern area. We also have some sites in the rangeland settings in the east. And we also have several irrigated and rangeland sites over in the west, over west of Lexington. Oop. Okay, it's responding now. Okay, so the data collection in the vadosone, the methods varied from the NAWQA program to what we did in the Central Platte. Originally, we did casing advanced drilling. We drilled without drilling fluids. These are some of the installations in Colorado. We used auger at all the sites in the Central Platte NRD. We got data about the lithology. We collected continuous core for soil hydraulic properties, water content, matrix potential, and KSAT. We also used several different tracers to estimate water flux using tritium, chloride, and nitrate. In terms of instrumentation, we use primarily heat dissipation probes that measure matrix potential, so we could get real-time information about total potential gradients and understand the direction of water flux. It's not always down in the vadosone. There are areas of the high plains where there's upward potential. We also had suction lysimeters here to measure nitrate, and we used a potassium bromide tracer I'll show you in a minute. We also have gas sampling ports to look at N2O, which I won't talk about today. It's kind of a mess putting these things in the ground. There's a lot of wires. But the data is really unique. We're getting, in this case, this is from Texas. This data is older. But what we see are real-time responses in the vadosone to weather events. In this case, this is a large rain and actually snow event in Texas, and we saw within the matter of days or weeks a response upwards of 7 meters, where previously we had seen no response in terms of water fluxes. So there's a really unique data set we've been collecting here. We have weather stations, we have nested monitoring wells at the sites. We're using remote telemetry to collect the data. It's sent back to the USGS office. Monitoring wells, we have pressure transducers. We also used a potassium bromide tracer to understand water fluxes in the near surface. So we came back and cored. This is Jeff, he's applying the potassium bromide tracer. And we came back at different time intervals to core and see how far the tracer had moved. We did a series of groundwater sampling, both for the quality, groundwater quality, major ions, nutrients, but also to date the water and understand residence times. We used dissolved gases, CFCs, tritium, helium, and SF6. So we used a series of field techniques to understand the recharge and water fluxes. We also used Hydrus 1D models. And just to very quickly tell you about the models that we developed, we have 4, 2 in the west, 1 under rangeland and 1 under irrigated corn, 1 in the east, 1 under rangeland and irrigated corn. Hydrus solves Richard's equation for water flux, variable water flux in the vadosone. So we use the field data, the soil hydraulic properties, and the tracer data to build the models and to help validate the models. We wanted to understand the irrigation demands on the corn, and we used the crop sim model that was developed here at UNL. Climate data, because we're interested in understanding how future climate might affect recharge rates. What we did with this study was compare a baseline of the year 1990. So we had 30 years of simulations centered on 1990, and then 30 years centered on 2050, so mid-century. We used 2 future climate scenarios, a warm and a low warming scenario. The low is equivalent to the RCP 2.6, it's the relative concentration pathway, and a high warming, the RCP 8.5. We're on the path right now to probably online with the RCP 8.5, and that'll come into play in just a minute. And we use an ensemble of 16 different global climate models, and this was prior to CMIP3, or IP5, so it was the CMIP3 data sets that we used. And so we used Hydrus then to simulate recharge and ET, and what you're going to be seeing then is a comparison of recharge rates from 1990 to the simulated mid-century 2050 data for the next series of slides. And before I get there, I just wanted to set the stage with some of the findings from the NAWQA study. And what we see is a really important control of land use, land cover, and climate gradients on recharge and water flux in these thick vadosones throughout the high plains. So what you're looking at here are 2 different sites in the top in the northern high plains, rangeland and irrigated corn, and then 2 sites in the southern high plains, again, rangeland and irrigated corn. These are plots of total potential versus depth below land surface. So total potential, like hydraulic head, water flows from high total potential to low total potential in the vadosone, the unsaturated zone. So we can see the importance of the regional climate gradients if we compare, if we look at the rangeland sites, first of all, in the northern high plains. We see a downward potential gradient, and using tritium and chloride mass balance, we estimate recharge around 70 millimeters per year, so about almost 3 inches per year. But when you compare that then to the southern high plains rangeland sites, we see a strong upward total potential gradient in both the wet and the dry seasons. So under current conditions, there's not a downward potential. Water varies in the root zone, but doesn't move downward beneath these profiles. And using chloride mass balance, we estimate recharge of about 0.2 millimeters per year. So effectively no recharge in major parts of the southern high plains. But what's important though is the effective land use land cover, that in the northern high plains under the irrigated cornfields, we see upwards of about 100 to 111 millimeters per year because of that irrigation return flow. But what's interesting then is in the southern high plains, when the land is converted from rangeland to irrigated fields, we can see a reversal of those total potential gradients and a downward flux, but still very low recharge rates of 17 to about 30 millimeters per year. Okay. So getting back to the Central Platte NRD, and so what we're going to look at first are the observed or historical recharge rates, first of all from the tracer technique. So we have tritium, chloride mass balance, the potassium bromide, and the groundwater dating estimates shown in the symbols here. under the rangeland and irrigated cornfields. These are for the historical 1990 period. And on top of those are the box plots for the simulations that we'll get to in just a minute. But generally what we see, that the recharge rates are primarily controlled by the land use land cover, and to a much lesser extent by that east-west gradient and average annual precipitation. So here under the rangeland sites, if you just key in on the symbols for the time being, generally recharge, whether it's in the east or west, generally below about 50 millimeters per year. Under the irrigated fields, from 50 upwards of over 200 millimeters per year. So that irrigation return flow is important in terms of increasing recharge rates. And then on top of that, we have the box plots here. I should point out the yellow are the western sites, and the blue is the eastern sites. And so each of these box plots represents the median of those 30 years of simulated annual recharge from the 16 global climate models. And so, first of all, it's good to see that our models are producing recharge rates that are consistent with our field-based estimates, so we feel good about using these models. And we also start to see influence of that east-west precipitation gradient, that we do see a statistically significant higher recharge rates under the eastern rangeland versus the western rangeland. It's not a statistically significant difference between the eastern irrigated corn versus the western irrigated corn, but the mean and median is higher under the eastern irrigated corn. Okay, so I just wanted to talk a little bit about the climate data that we're using to forecast future precipitation ET recharge. We used a total of 16 global climate models, which in hindsight is probably overkill, but we're using an ensemble approach because there's a lot of inherent uncertainty if you used any individual one of these GCMs. So just to kind of illustrate that on the top, we have changes in average annual precipitation from 1990 to 2050 under the high warming scenario. And we see ranges of plus or minus about 20%. In terms of future precipitation. It's only about plus or minus 7% under the low warming scenario. But this is pretty common now that we're using ensemble approaches to understand how hydrologic responses to future climate, because if we picked any single one GCM, they would be biased either potentially low or high depending on the assumptions that are used in any one of those models. So that's why we're presenting these results in a probabilistic framework. So if we summarize that past slide to look at future precipitation by mid-century, again, what you're looking at are east and west, west in yellow, east in the blue under the low and high warming scenarios. And this is the change in total annual precipitation by mid-century. So what we see from the GCM output is a statistically non-significant increase in average annual precipitation by mid-century under both the low and high warming scenario. So under the low, we see, whether it's the eastern or western, we see about, just looking at the median values, 1 to just over 2% increase in precipitation by mid-century. Under the high warming, the eastern about 6% increase, and the western about less than 1%. So a statistically non-significant increase in precipitation, although it might be wetter by mid-century. So what does that mean for future ET? Taking the temperature, forecasted temperature from the GCMs, running that through Hydrus, using the Penman-Monteith equations for ET estimates. What we see, the results indicate a statistically non-significant increase in average ET by mid-century for the low warming, but a statistically significant increase in ET for the high warming scenario. So if we start just here with the low warming scenario, whether it's the rangeland or the irrigated east and west, the models are indicating less than about 2% increase in ET. And this one I want to point out, the eastern rangeland, some of the models actually indicate a decrease in ET rates, which will come into play in just a minute. But we do see a statistically significant increase under these high warming scenarios. In rangeland settings, 20 to about 26% increase for median ET, and under the irrigated fields, about 13 to 15% increase in ET. Irrigation, future irrigation demand, we used a regression approach to estimate output from the crop sim model. And what the models are indicating is a statistically significant increase in the irrigation demand under both the low and the high warming scenario, about a 1 to 2% increase under the east and west sites, and 14 to 15% irrigation demand under that high warming scenario. So what does it all mean for recharge? So what we see, it's a little bit more complicated, that we see a statistically non-significant decrease or increase in that average recharge under the low warming scenario, so we'll go over that in a minute, but a statistically significant decrease in recharge rates under the high warming scenario. So here under the low warming scenario in the rangeland, that's about, the median is around 9 or 10% decrease in recharge. Because of that decreased simulated ET, the eastern rangeland sites, the models are actually projecting a slight increase in recharge rates by mid-century. And then if we go over here to the irrigated sites, under the low warming, about a 10 or 11% reduction or decrease in recharge rates. So what's really eye-opening when we ran these models is what happens under the high warming scenario, that here under the rangeland sites, specifically under the western site, the models are indicating about a 98% decrease in terms of the median recharge rates by mid-century. And the eastern area, about 50% reduction, and under the irrigated fields, anywhere from about 30 to 45% reduction in recharge rates. So by mid-century, there could be very large reductions in recharge for parts of the Central Platte NRD. So to try to summarize some of these findings and some of the conclusions, generally what we're finding under the low warming scenario, which we will likely exceed by mid-century, there are differences. They're not statistically significant differences in precip, ET, recharge, possibly irrigation demand. But the real, I think, concern, especially from a management perspective, is where we're heading under the high warming scenario. We have potentially large changes in precipitation ET, and specifically these recharge rates, especially this almost 100%, 98% reduction in recharge under rangeland diffuse recharge in western parts of this Central Platte NRD. So there seems to be, one of the take-home points, there seems to be a tipping point or a threshold somewhere between this kind of low warming and high warming scenario where we're seeing potentially large reductions in recharge by mid-century. So some of these findings were consistent with what we found throughout the rest of the high plains, that there tends to be an inverse relationship between average annual air temperature and recharge rates, kind of mimicking that north-south gradient that we see through other parts of the high plains. And there's, of course, a positive relationship between precip and recharge along that east-west gradient along the northern high plains. But I think what's new here in terms of recharge specifically is we're seeing a bidirectional shift in changes of climate, local hydrology, and impacts on recharge. So we have more of a warming northward and drying eastward throughout the high plains, and specifically the northern high plains. By mid-century, air temperature and recharge rates of the northern high plains could be comparable to present-day central high plains hydrology and recharge. What we found specifically is that mid-century recharge in the eastern part of the Central Platte and maybe other parts of Nebraska are comparable to present-day recharge in the western part of the state. And specifically, the western study area in Nebraska and the Central Platte will be much more like present-day southern and central high plains in terms of recharge rates. So what it seems to, the models indicate that the changes in recharge are less a function of future precipitation and much more sensitive to changes in air temperature and ET patterns. So from a management perspective, you know, the concern when you look at those water table decline maps and the challenges that other parts of the high plains face, I think the challenge and the concern for the northern high plains is that it's going to become, in terms of climate and hydrology, maybe recharge more like the central high plains. So we need to be thinking about management and adaptation strategies to deal with future reductions in recharge, which may have impacts on lower water levels, groundwater storage, impacts on environmental flows. So maybe this is a somewhat simplistic plan, and I think things NRDs are already working on is in terms of adaptation, it's really important to communicate, to have educational opportunities among the NRDs, among the managers in the different regions. With this bidirectional shift, it might be important for managers in the east to think more about what's successful in the western part of Nebraska, and western Nebraska maybe communicate more with Kansas and the central high plains of what works down there, because our climate will become more like Kansas. So that's it for that part of the talk. If I'm going to leave time for questions. This paper I presented is in Agricultural Water Management. It was published last year. So I can send people that, or you can find it yourself. There's a lot of details from this study in this USGS report that Greg Steele was the lead author on, so a lot of the raw data sets are available through that report. And then the High Plains NAWQA study, the summary report, if anyone's interested, is this document here. So email if you want additional details about those studies. And the last thing I want to mention, a little bit of advertising. As Dan mentioned, I lead an international program about research, education, and outreach about climate change impacts on global groundwater resources. To my knowledge, we're the only program that works on a global scale addressing these issues. And what we are is a network. We promote projects and papers and collaboration. We have lots of training workshops and opportunities for students in the audience. So I'd encourage you to go to the website, and we're always looking for colleagues and collaborators. We're going to be, if anyone's going to the IAH meeting in September, the International Association of Hydrogeologists, we're going to be having a workshop there. And then we have another project that's just starting this year. It's a 5-year study that it's going to be promoting training workshops about groundwater modeling and climate modeling and water energy food nexus modeling. That's a partnership with myself and colleagues in Southern Africa. There's a few countries there, and then colleagues in the Mediterranean. So there's going to be a lot of opportunities for students with these workshops that will be coming up over the next several years. So send me your email and join our mailing list, and we can send you more information. All of our publications and information is up on the website. Okay, so what I wanted to do then with the remaining time here is to tell you a little bit about what's going on with groundwater management in California and give you a little bit of history and where we are today. I think there's some really interesting things going on from what I know about Nebraska groundwater management issues. And so where we're going to start is about 5 years ago with 2014 in California. And it was dubbed the Year of Water in California. And I just picked a couple quotes from local newspapers. Most significant year for water and generations, a critical turning point in California's water history. So this is Jerry Brown, the governor of California. And he's signed some important legislation that we'll get to in just a minute. So California, it's a little bit unique in terms of the climate, different than Nebraska, but there's still an important gradient in precipitation and air temperature, that most of the rainfall, most of the runoff is in the northern part of the state, much drier deserts in the southern part. And about 90% of the average annual rainfall and runoff occurs only about in 40% of the state, and the remaining 10% is over about 60% of the state. So there's a big disparity between the water availability, generally in the north, and then demand for water, especially in the Central Valley and the southern San Joaquin Valley here, and certainly in LA and in Southern California. So most of the conflict in California originates from this simple fact that the water is all up here, but people and farming is down here. So the way California grew was these massive engineering projects where big aqueduct systems, the Central Valley Project, we diverted that surface water, we collected it in reservoirs, and canal systems brought it to southern parts of the Central Valley, and the State Water Project later in 1960 brought water further down to LA and Southern California. And so this is a simple map of most of the major water projects, the aqueduct systems. These were all built decades ago, 50, 60 years ago. Really important for the agricultural economy, the urban economy, but they're degrading, they're crumbling. There's a lot of impact from earthquakes. But because of drought and climate change, they're far less reliable in terms of surface water availability. So what happened specifically in 2014, California found itself in the middle of a drought. It started in 2012. It technically ended in 2016. It was the worst drought on record for California. Most of the state was in extreme drought conditions. It was the driest year on record, and there were dendrochronology studies that it was the worst drought in about 500 years based on those tree ring studies. So very significant drought. Surface snowpack was abysmal. The reservoir levels, these are the major reservoirs around the state, and you can see that the water levels were below capacity, far below historical averages. And not to get into it too much, but this system was really designed, the surface water system was designed for about 17 million people back in the 50s and 60s, and the population's doubled now. So the surface water reservoirs, the canals don't really meet the demand around California. I mentioned the snowpack. In 2015, the snow water equivalent statewide was about 5% of normal. The managers were panicking at this point. Ultimately, what happened, surface water deliveries in some places were cut by thirds. Some farmers received no surface water deliveries. Reservoirs were dry. Huge impact in terms of the economy from the drought. I just mentioned the Central Valley farmers. Early parts of the drought received about a third of their water deliveries. By the end, some were receiving no surface water deliveries. This is a study by UC Davis. It had an impact in terms of groundwater pumping increased dramatically, as I'll show you in a minute. A cost of around $450 million to replace that surface water from groundwater pumping. Thousands of acres went fallow. 15,000 jobs were lost. Higher unemployment. So big impact, about $2.2 billion in total economic losses during the drought. So that was the one thing that happened in 2014. Also the governor, there was some state leadership. The governor put out a water action plan, things like conserving more water, fixing the San Francisco-San Joaquin Delta, better managing groundwater. And I won't dwell on this too much. Throughout the drought, what happened was the public became more aware of a lot of the water issues around the state, and we voted on a general bond, a water bond that passed overwhelmingly. About 67% voters supported it, over $7 billion bond to go towards improving water storage, improving watersheds and flood management, safe drinking water, and money for local water resources, including the next program I'm going to talk about, which was the Sustainable Groundwater Management Act. So California is one of the last states to have comprehensive regulation about groundwater management. And this passed. And so it's, I think, a really classic example here of where there's crisis from the drought. The public became aware from simple things like the reductions in watering their lawn, their fines. Urban areas really had to cut down on their water use. And ultimately that catalyzed this action that people were ready to put forward the regulations about SGMA. So it passed, it went into law, it took effect in 2015. And, you know, I mentioned the drought. We'll start over here on the right. That period of the drought we saw in places over 30-meter declines. These are water level declines at individual wells in many parts of the Central Valley, along the coast. There's a lot of farming in these very productive agricultural watersheds along the coast. There's seawater intrusion issues around Southern California and LA. So California, because SGMA was passed, it's starting to now deal with its version of the global groundwater crisis. So we have overdraft conditions, wells that are failing. I mentioned seawater intrusion, a lot of water quality problems. There's estimates of over 1 million people throughout California that lack access to clean, safe drinking water, which is kind of hard to believe. In a place like California, there's a lot of subsidence issues. The ground is sinking in parts of the southern, in the San Joaquin Valley, parts of around San Jose and other places. There's been large reductions in discharge to groundwater-dependent ecosystems, but yet we have this, you know, $47 billion ag industry that's heavily dependent on groundwater, and then no comprehensive regulation. So that was all changed with the passage of SGMA. And what it does is the state provides guidelines and basically a backstop, and provides the power to these local agencies to best manage their water resources. The state had prioritized, there's over 515 groundwater basins around the state, prioritize them on either they were critically overdraft, if they were adjudicated basins, or high, medium, low to very low. And so all the high and medium priority basins have to comply. It's mandatory to comply with SGMA. And that accounts for about 127 basins around the state and a little over 95% of all the groundwater use statewide. So the timeline, what's been happening since 2015, by summer 2017, new groundwater sustainability agencies, or GSAs, had to have been formed. And typically what happened was existing water agencies came together and kind of have new names of GSAs, but they tend to be just the older water agencies. And since then, there's 146 new groundwater sustainability agencies and over almost 270 local agencies participating. So this is a massive effort across the state. And then what they have to do are develop these local groundwater sustainability plans. If they're a critically overdrafted basin, they have to have the report go through a public approval process submitted to the state by the year 2020. And so with a 90-day review timeline, most of these GSPs have to be submitted by about August or September of this coming year. So there's been a lot of work, and it might not, I know it seems a little backwards that the most critically overdrafted basins have to go first in terms of coming up with sustainability plans, but that's the way it's written. And then the other high and medium priority basins have to submit their GSPs by 2022. And then they have to implement those by the year 2040 or 2042. They have to show milestones, measurable objectives at 5-year increments. If they're not, the state will come in and manage the system. And none of these agencies really want to go that route. They prefer to keep the local control. So what SGMA provides that's been pretty unique in terms of California anyway, these GSAs have the tools and the legal authority now to do things like to collect water levels, to collect pumping data, to impose possibly pumping fees or augmentation fees to groundwater users. They're going to have, there's some teeth for these local agencies to enforce the terms that are agreed upon. There are some funding mechanisms, part of that Prop 1 that I mentioned. At least initially there was around $100 million for these GSAs to apply to get funding to put together the GSPs. They have to go through a stakeholder process, so it's designed to be a transparent, stakeholder-driven approach, so there has to be there's many disadvantaged communities throughout California, and so to make sure all the different interests are accounted for in these GSPs. And the unique thing about SGMA is that it gives a definition to what sustainable groundwater management is, at least for California. And so they have to, during this planning and implementation phase, and even beyond the 2040, 2042 timeline or horizon, they have to deal with these undesirable results. And they're keyed on these 6 different sustainability indicators. So they have to decide what is an undesirable result in terms of lowering of groundwater levels. What's undesirable in terms of reduction of groundwater storage, coastal areas, and even some of the inland areas. Seawater intrusion or upconing of salt water from brackish units is a big concern. Groundwater quality, subsidence, and this is going to be trickier to deal with, but where there's groundwater surface water interactions, and to make sure that there's groundwater base flow or discharge to support groundwater dependent ecosystems. So it's up to each of these GSAs to decide what is undesirable in terms of these 6 indicators. So that's just a little teaser. There's a lot of information for you managers or researchers if you want to learn more about SGMA. The state's been pretty good with putting out guidelines and report documentation of what these GSPs need to look like. So I'd encourage you, if you want to learn more, go there. And just to throw out, if there's any managers or if there's a groundwater delegation from Nebraska, maybe if you want to come to California, let me know, and we can set up meetings with some GSAs. Might be a good, learning or networking opportunity. And maybe next winter, when you're having your blizzards in January and February, you might want to come to California for some good weather. So with that, thanks for the time, and I think I left some time for questions.
Hi, I have a question about the simulation you made using Hydrus. And it seems that you're using the free drainage as the lower boundary condition. And I just wonder, in the future, so groundwater level will continue declining or maintain the current stage. Have you considered how the future climate change will impact the groundwater level, and how the change of groundwater level will change your simulation? Will that, if your groundwater level will be lower, will that affect your recharge estimation?
Yeah, that's a good point. We do use the assumption of free drainage at the bottom of the simulation. So it doesn't simulate a water table, and we're not simulating a water table decline. But I think the simple approach is the water flux at the base of those models we would assume would eventually become recharge, even if the water table now by 2050 is meters below. That water flux at the base of the model will eventually become recharge.
I'm just curious, you said something about over 1 million people don't have access to clean drinking water. And what's the problem there? Is it contaminants? Is it no wells?
Yeah, I think a lot of it is groundwater quality, nitrate in agricultural areas. There are some issues with arsenic, hexavalent chromium, uranium in certain parts of the Central Valley. But a big issue are these disadvantaged communities, these typically rural communities. Many people that are not on municipal water supplies, that are on domestic wells, and they don't have the resources for either the testing or the knowledge or remediation programs. So it's more of these ag communities, rural areas. And probably there are certainly water quality and groundwater contaminant issues in urban areas, but the municipal water suppliers meet EPA, MCLs. So
I don't mean this as a frivolous question. Do you think your modeling results are good news for advocates of the Buffalo Commons?
Advocates of the Buffalo what?
Buffalo Commons? That the High Plains should be really move back to a ecosystem status that's more sustainable in a way that we don't typically think about? And I just use that as a metaphor for thinking differently about what we do here.
Yeah, I'm going to sort of punt on the details of the Buffalo Commons because I don't know enough about it. But, you know, most parts of the country are going to have significant changes to their climate, local hydrology, and I think it's really up to the local communities to decide how to manage their resources and their land, and hopefully to use the science to make the best informed decisions. And it's hard to plan out to the year 2050. Most of the planning horizons for managers or infrastructure is much shorter term. So it's going to be a challenge to think long term, but also to deal with present day issues with like 1 million people with lack clean water, climate variability, of issues with flooding. So I don't know specifically about the Buffalo Commons, but I'll let you local community members decide on how the groundwater and the farming practices should be done here.
Your bidirectional shift of recharge and associated factors in Nebraska is really interesting and frankly a little bit terrifying to those of us here in Nebraska. I guess I'm wondering, given everything that's going on in California, are there similar efforts to try and model those perhaps future changes in recharge? And the local entities tasked with dealing with that, are they getting on board that wagon and trying to figure out what might happen in that regard?
Yeah, so there are some efforts. Some of from the research community, UC Davis, they have some larger scale models over larger parts of the aquifer. But each GSA, they have to understand and quantify their water budget. And most of the GSAs are using mod flow models. And so the state is providing a uniform data set for future climate. It's all downscale data. So, typically it's consultants building these GSPs for the GSAs. And the consultants will be using, in many cases, local mod flow models, or sometimes they're telescoped from larger USGS models. But they are, in the GSAs I'm familiar with, they are thinking about future climate. Maybe not out to 2050 because they really have to hit the 2040 mark. But yeah, I can't think of a paper or a study that's shown that bidirectional shift or a large regional shift in recharge in California. Maybe that paper needs to be written or done.
I have a quick question. What happens if a groundwater management area doesn't meet its metrics for sustainability?
That's a good question. I don't know if you miss the mark. I think the state will come in after that 5-year review period, and I don't know that they would jump in and take control if you miss the mark over that one milestone. I don't know what happens if you missed a second milestone. I don't know. There's a lot of questions, and I don't know exactly what the state would do there.
I think this probably applies more to California than Nebraska, but as water gets more expensive in California, wouldn't that limit the use? And so your models would be overly pessimistic if you look at a decline in, like, for example, water tables.
It's possible, yeah. That's a good point, a valid point. As some of these GSAs start charging pumping fees or augmentation fees, in the basins that I'm familiar with, where there are augmentation fees, the charges are on the order of about $200 to $300 per acre foot. So it's not much, and it's not an economic incentive for farmers to pump less. I mean, they want to ensure the health of their crop, and they put more water on than they need. So I don't know I'm not an economist, but what price would you have to put on the water to really curb the use? And so we'll see what some of these agencies decide to do. I'm not sure. We'll see.
All right, well, let's thank Jason once again.